In this video, we'll look at some additional optimization questions. For this example, you are designing a rectangular container, and the rectangular container has an open top. Think of those large things that you've seen at a construction site. You're asked to design it so that the length of the base is 3 times the width. Let's see if we can draw a picture of that. Here's your container. Again, it says that the length of the base is 3 times the width. So let's let the width be denoted by x. Then the length is going to be 3 times that width, and hence 3x. And we'll also denote the height by h. Now you're also told that it can hold 3,000 cubic feet of materials. That's the volume, so let's go ahead and use the idea of the volume. Remember, the volume is length times width times height. We'll say the length is 3x, the width is x, and the height is h. So we get 3x squared h. And remember, it said 3,000 is the volume of this. So that gives us a constraint. We'll come back to that in a moment. Now we're also told the material for the sides costs $15 per square foot, and the material for the base costs $20 per square foot. We're going to need to get some sort of surface area calculation that's going to give us our costs. Let's write down $15 is going to be for all the area of the sides. Let's do it this way. Your 4 sides are a front and a back, which is x times h. So I'm going to say 2x h. The left and the right are 3x by h. So I'm going to say 2 times 3x times h. And then it's $20 for the base. And the base is x by 3x. That'll give us our cost function for how much it will cost us to build this container. Now we can simplify this. If I simplify inside the parentheses, I've got 2xh plus another 6xh is 8xh. And then I've got a 20 times 3 is 60x squared. So 15 times 8 will give me 120 xh plus 60 x squared. That will give me the cost associated with building this container. Now we need to use our constraint. My suggestion would be to solve for h. So on this side, I'm going to divide both sides by 3x squared. If I do that on both sides, then I just get an h. H is equal to, the 3,000 divided by 3 I'll write as 1,000, and this is over x squared. Now let's make our substitution. We have 120x, and h is now 1,000 over x squared plus 60 x squared. If I simplify that, I get finally that my cost function is 120,000. Let's write this as x to the negative 1 because we're going to take its derivative, and we have 60 x squared. Let's take the derivative over here. C prime would be negative 120,000 x to the negative 2 plus 120x, and then I'll set it equal to 0. The technique that I think will help us the most to go forward with this is let's multiply both sides by x squared to get rid of the x to the negative 2. That will give me negative 120,000. The x squared and the x to the negative 2 cancel out. Plus 120, the x squared and the x give me an x cubed. And I get that this is equal to 0. Now I'll add 120,000 to both sides, which gives me 120 x cubed equals 120,000. Divide both sides by 120 to get x cubed equals 1,000. And then finally, I get x is equal to 10, and this is in feet. You might also make it worthwhile to say that 3x then would be the length of 30 feet, and the height was given by 1,000 over x squared, which would be 1,000 divided by 100, which is also 10 feet. Now really what we need to do at this point is take a second derivative and make the claim that this is actually the minimum. At this point, we will skip that step, but keep in mind that for every optimization problem, it is a part of ensuring that you actually have found the actual minimum or maximum. This means the container should be 10 feet by 30 feet and 10 feet tall for a total cost of $18,000. And to get that $18,000, you can simply take your values of x and h and put them into the cost function that we have right here. Our next example is going to use the distance formula. We want to find the point on the line 6x plus y equals 9 that is closest to this point, -3, 1. Here's a picture of what we're looking at. We want to find the distance, the shortest distance between this point and this line, which is just somewhere along the lines of what would actually be perpendicular if my graph were actually drawn with the same x scale and y scale. But what we're going to do is calculate that distance and minimize that distance. To do that, we're going to need the distance formula, which is the square root of x2 minus x1 squared with y2 minus y1 squared. I'm going to let the -3, 1 be my x1, y1, and some arbitrary point xy be my x2, y2. And when I do that, the x and y will satisfy the relationship of the line that we have drawn here. So that equation is actually our constraint. Further, I'm actually going to do something a little bit different. I'm actually going to minimize d squared. That way I don't have to worry about the square root. In doing that, I'll actually find the minimum value for d, since all of this is positive numbers. Let's plug it in, and again I'm going to ignore the square root. We'll call this thing capital D, which is really d squared, and I've plugged in my x1, y1, and my x2, y2 into the formula. Now I can write this as x plus 3 squared, but then for the y, let's actually take our constraint, which was the equation of the line, and get something to do with y in terms of x. I know that 6x plus y is equal to 9, so I can get y is equal to -6x plus 9, and I'm going to use that in my formula. Now let's just start simplifying. I get x squared plus 6x plus 9. The second one is 36x squared minus 96x plus 64. This gives me a final equation of 37x squared minus 90x plus 73. Now I can take this derivative and set it equal to 0. So this capital D, which again is a square of my actual distance formula, I get 74x minus 90, and I'll set that equal to 0. 74x minus 90 equals 0. Add 90 to both sides to get 74x equals 90, and so x equals 90 over 74. Again, you should use the second derivative to verify that that is the shortest distance, but we will skip that step this time. And then to find your y, you'll simply plug that back in. Even though it's a little bit heavy on fractions, we can get this. And I get 126 over 74. If I were to draw this on my graph, 90 over 74 is just a little bit bigger than 1. And 126 over 74 is also just a little bit bigger than 1, but a little bit larger than the other one. You'll notice this means that my picture looks pretty far off, but that's because the 90-degree angle that I said would work is a little bit funky on this scale that I have. Finally, to write our sentence, the point closest to -3, 1 on the line 6x plus y equals 9 is 90 over 74, 126 over 74. Here's an interesting business example that will show you how to maximize a profit given some demand information. There's a lot of details to this one, but let's just see if we can make it all work out. Terry makes and sells necklaces on the beach. He finds that when he sells them for $10, he gets about 20 a day. And if he sells them for more, then each dollar more he charges reduces his sales by 2. It costs him $6 to make a necklace, and we want to figure out what is the price that will help him make the most money. So to do that, we're going to start out by working on the demand a little bit. I'm going to call my price for my X and the quantity sold my Y, which gives me 2 points. I can get 10, 20 as a first point. And then another one, you could kind of see what the slope is, but I'm just going to go with an intuitive $1 more, 2 necklaces less. And then we could find an equation for this demand that we're looking at here. First, find the slope. 18 minus 20 over 11 minus 10 is -2. You might not be surprised to see that because it's 2 sales lost for every dollar increase. Then we can plug it into the point slope formula with whichever of these points we want. I'll choose the first one. Say y minus 20 is -2 times x minus 10. That gives me y minus 20 is equal to -2x plus 20, or y is equal to -2x plus 40. That is the demand function. And so this says how many necklaces he will sell given the price that he's charging X. So now this is a little bit complicated, but now we can figure out how much money he'll make as well. The revenue that he would make would be the price that he is selling them for times the number of necklaces he can sell at that price. So I can change this to X times -2x plus 40, which would be -2x squared plus 40x. That's the revenue. Now for the cost, this is a little bit easier. It costs him $6 to make each necklace, and he's selling Y necklaces a day, so we can plug the Y function back in, say -2x plus 40, and get that the cost is equal to -12x plus 240. Finally, we can generate our profit function. The profit function is revenue minus cost. So this gives us -2x squared plus 40x minus -12x plus 240. And if I simplify that, I get that my profit function is -2x squared plus 52x minus 240. Same as usual, let's take the derivative and set it equal to 0. The derivative would be -4x plus 52. So if I set that equal to 0, I can subtract 52 from both sides to get -4x is -52. Divide by 4 and get x is 13. That is the value that I wanted. Terry should sell the necklaces for $13 each to maximize his profit. This next example borrows a little bit from the last example in that if you take the price per unit times the number of units, you'll end up with the revenue function. So let's jump right into that. You've got a demand function given to you, and so I want to calculate the revenue, which would be the price times the number of items sold for that price. We'll plug in our P, which is 56 e to the -0 point, that's a lot of zeros, 2, 3, 4, 1, 2, x, and then that is times x. So let's simplify this thing. Let's use this as my first, and this as my second. And so then r prime would be the derivative of the first times the second plus the derivative of the second times the first. When I take this derivative, I get 56 times this e plus, let's take a small shortcut here. This technically needs the chain rule, but I'm going to use a little formula for e to the kx being k e to the kx. That actually makes this plus a minus, and I say all these zeros is my k, my coefficient, and the e term. Again, times 56x. I want to set this derivative equal to 0. And when I do, I'll do my usual and factor out the e here. That leaves me with the 56 minus, and then if I multiply these two together, I get 0.000672x squared, simply by multiplying my 56 times that small decimal. And there's two x's to make the x squared, and again I'm setting this equal to 0. Just like the last e example, remember that e to any power is always a positive number. So consequently, this thing does not contribute to anything with what we're trying to do. We'll simply set the other part equal to 0. Let's add the decimal times x squared to the other side. Divide both sides by the decimal to get x squared equals 83,333, and it's actually a repeating decimal, but I'll just say 33. Take the square root to find the price of approximately $288.68. The maximum revenue occurs when the price is $288.68. The last example will do something similar with looking at demand and revenue, and again we're wanting to maximize the revenue. So let's start off by using what we have. If you have $800 a month as the rent, all units will be occupied, all 100 of them. Let's do the same thing with calling my price x and my number of apartments y. So the all in this case is 100 for this particular example. $800 gives all 100 being filled. And now if the rent is increased by $10, one unit will remain vacant. You can probably get the slope out of this, but let's just increase the price by $10 and remove 1 from the number of units that will be filled. And now let's calculate the equation of this line. That'll be our demand, which we can then create the revenue and maximize. We'll start with the slope, which is 99 minus 100 over 810 minus 800. That gives me negative 1 over 10 as my slope. And then let's use the simple one. Y minus 100 would equal negative 1 over 10 times x minus 800. That gives me y minus 100 is negative 1/10 x plus 80. And so I get y equals negative 1/10 x plus 180. That's the demand equation. And just like last time, the last two examples, we're going to say r is equal to xy and plug in our y. Y is negative 1/10 x plus 180. Multiply that out to get negative 1/10 x squared plus 180x. That's our revenue function. Now let's take the derivative and set it equal to 0. R prime is equal to negative 1/10 times 2 is 1/5, and I still have an x plus 180. Setting that equal to 0, I can then subtract the 180 from both sides to get negative 1/5 x is negative 180, and then I'll actually multiply both sides by negative 5 to get x is equal to 900. And that's a price, so that would be in dollars. What this means is the maximum revenue occurs when units are $900 per month.